Welcome to the Explainer. Today, we're tackling a pretty mind-bending question. What's the real difference between a quantum computer and a supercomputer? And I'll give you a hint, it's not just about being faster. It's about a fundamentally new, almost alien way of looking at a problem.
Okay, so to really get this, we first need to understand the kind of problems we're up against. We're not talking about your average spreadsheet. We're talking about challenges so ridiculously complex that if you gave one to the world's best supercomputer at the moment of the Big Bang, it still wouldn't be done today. It's kind of like trying to find one specific grain of sand on every beach on the entire planet.
So how do we handle these monster problems right now? Well, the classical approach is pretty straightforward. If one computer isn't enough, just throw more computers at it.
And that's parallel computing in a nutshell. We take a gigantic task, say simulating a new drug molecule, or modeling the entire global financial market, and we chop it up into thousands of little pieces. Then we give each piece to its own processor to work on at the same time. It's the ultimate divide-and-conquer strategy.
And we're talking about massive operations here. Clusters with tens of thousands of processors all cranking away in parallel. It's incredibly powerful for sure. But here's the catch. At the end of the day, you're still just adding more individual workers. But what if? What if there was a way to make them all work together, not just side by side, but as one single, interconnected entity?
All right, now let's take that leap into the quantum realm, which has a completely different playbook. And it all starts with its most basic building block, the qubit, which pretty much just throws the old rulebook out the window.
You know, a regular computer bit is basically a light switch. It's either on or it's off, a 1 or a 0. That's it. A qubit, though, a qubit is more like a dimmer switch. It can be on, it can be off, and it can be every single shade in between all at the same time. This wild property is called superposition, and it's where the quantum magic really begins.
And here's where things get wild. See, 6 regular bits could hold exactly one number out of 64 possibilities at any given time. But 6 qubits, thanks to superposition, they can hold all 64 of those possibilities at once. That's not just a little bit better, that's a whole different ballgame. We're talking about exponential growth, and that right there is the engine of a quantum computer's power.
Okay, so you've got this incredible power, this cloud of all possible answers existing at the exact same moment. What do you do with it? Because on its own, it's not actually that useful. If you just took a snapshot, you'd get a totally random answer, just noise. So how do you get all those possibilities to work together to find the one right answer?
And that question, that's the one that leads us to the real magic trick. This is the secret ingredient that makes a quantum computer truly, well, quantum.
It all comes down to a property that even baffled Einstein. He famously called it spooky action at a distance. We call it quantum entanglement. And this is what takes that chaotic cloud of possibilities and turns it into a single, focused, problem-solving machine.
You know, there's this fantastic analogy from our source material that just nails it. It's like that old kid's book, Swimmy. Superposition gives you a whole school of little fish, each one representing a different possible answer. But entanglement is the magic that makes them all swim together, in perfect sync, acting like one single giant fish.
So what's happening is that entanglement literally links these qubits together with an invisible thread. They're not on their own anymore, they're a single interconnected system. Their fates are tied. If you measure one, you instantly know something about all the others it's entangled with, no matter how far apart they are. This forces all those possibilities from superposition to cooperate, to interfere with each other, canceling out the wrong answers and amplifying the right one until they all converge on the solution.
Okay. Let's put it all together. Let's do a head-to-head comparison and see just how different these two worlds really are.
And this really breaks it down, right? On one hand, you've got classical computing, with its independent workers dividing and conquering. Its power grows proportionally. Add a core, get a bit more power. On the other hand, you have quantum. Its basic units are interacting entangled qubits. The processing is holistic. The whole system works together as one giant interconnected brain to solve the problem all at once. And its power scales exponentially.
This chart really drives the point home. Classical scaling is like climbing a staircase. You add a step, you go up one step. Quantum scaling is like launching a rocket. Every single qubit you add can literally double the machine's entire computational workspace.
That is the game-changing, decisive difference.
So you see, this isn't just about making faster computers to do the same old things. This is about inventing a completely new way to compute, a new tool for a new class of problems.
You know, a classical computer just crunches through instructions, one after another. But as our source material points out, running a quantum algorithm is, well, it's different. It's less like calculating and more like setting up a really precise physics experiment, hitting go, and then watching to see how all those entangled possibilities collapse and converge into a single answer.
So, here's the final thought to leave you with. Are we moving past an era of pure calculation and into a new age of computation as experimentation? This is a huge shift in thinking, and it might just be the key to solving some of humanity's biggest puzzles, from creating life-saving medicines to designing revolutionary new materials. The quantum future isn't some far-off sci-fi dream. It's unfolding right now, and believe me, it's just getting started.